We've just learned how precise scanners can be used to detect people and objects between people and people, or to do a risk infection here. But is this also working between ship to ship or ship to port, Henrich?
And the answer is yes, and we are very happy now to have the next presentation from Robert Zierat, and he will explain us how to use LiDAR scanner in anti-collision systems for ship-to-ship or ship-to-port infrastructure. And he will also explain us about the application of the LiDAR-based ship localization. Hello Robert, hello to Hamburg.
Hello Henrich, hello Ramona, moin from Hamburg. Yes, as you said, it's not only ship-to-ship application, it's also ship-to-land application. Oh. And it's quite similar to your park assistance in your car. But as we all know, ships are quite larger than cars, so there are some additional challenges to solve here. I prepared something for you to get more in detail on that. Have fun with it.
Of course, our LiDAR sensors can also be used for other applications. In the previously described application, the distance between two people was measured. But you can also look at such situations in a similar way, but on a larger scale. For autonomous shipping, the distance measurement and collision avoidance between two ships is an important task. And of course, also collision avoidance between ships and structures on shore. In Lower Saxony alone, millions of dollars worth in damage are caused to port structures every year. These damages can be caused in very different ways. Sometimes the maneuvering areas are quite confusing. Sometimes weather conditions make maneuvering difficult. And sometimes technical or human failure is the main reason for serious accidents. Regardless of this, collisions usually become very expensive. There are immediate direct costs and losses from direct damages to the ship and to the port. Often there's also financial secondary damages due to tailbacks and necessary detours for other ships. A very popular example from this year is the Ever Given, which caused hundreds of billions of dollars in losses by blocking the Suez Canal for 6 days. But even in the case of smaller damages, it's usually difficult to clarify who is actually to blame for the accident. Who should pay for the damage? Which insurance company will pay? How can a solution be found as soon as possible? So all stakeholders in the maritime environment have an interest in making maritime traffic in port areas more transparent, and they have interests in avoiding collisions wherever possible, of course. As in all real-world scenarios that need to be captured via digital systems, you need the right sensor technology to do so. Anti-collision systems for ships require long-range sensors because, at the one hand, large areas have to be monitored, and at the other hand, depending on their size, ships sometimes have very long stopping distances and also long reaction times. Here we have some LiDAR sensors that can be considered for these applications. Let's start with the LDLRS. This is a 2D device with a field of view of 360 degrees, and is currently the LiDAR sensor with the largest range in our 2D and in our 3D product range. To illustrate what the sensor is able to do, I've brought this small cube here with me. The outer edges are 30 centimeters long. It is black and reflects light very badly. The LDLRS detects this cube in a distance in up to 120 meters. That's more than the long side of a soccer field. The range on brighter targets is even up to 250 meters. This sensor here is the MRS 6000. It has not only one horizontal scanning layer, like the LDLRS has, but it has 24 scanning layers. The range is 30 meters on dark targets, like this cube, and up to 65 meters on bright targets. This sensor is characterized by the fact that these 24 layers are aligned without gaps, and so a gapless scanning over the entire horizontal and the vertical opening angle is possible. But we will take a closer look at what this is really important for in the next presentation. This is the LDMRS, and it's also a 3D device. It's available with up to 8 scanning layers. These layers are arranged with some gap to each other, but the detection range here is larger than that of the MRS 6000. It can detect black targets in up to 50 meters and white targets in up to 150 meters. Like all LiDAR sensors shown here, the LDR-MRS is very robust against environmental influences. It's equipped with software features and has very reliable measurement technology. Radar technology can also be used to great effect in the maritime sector. Here you can see the new RMS 1000, a powerful and, as you can see, very compact radar sensor. But let's come back to our cube here. Even if the visibility is very low, for example in very heavy fog or rain, this RMS 1000 would detect this cube reliably in up to 100 meters. So you can see SICK is already well positioned for the further automation of the maritime applications. But now I would like to talk about the future. SICK is part of a research project called SmartKai. This project is funded by the German government, and the goal is to develop an assistance system to prevent damages to ships and the harbor infrastructure. Very interesting and important project partners are involved, who have a great interest in solving this problem due to their fields of applications. But what is SmartKai and how does it work? We want to make maneuvering in ports safer. That means collisions should be prevented, the processes in the port should become more transparent for all involved parties, and, in particular, the pilots shall be supported during the docking process. We want to make that possible with several LiDAR sensors, which are permanently installed on the land side. And this is quite special and makes it different from other approaches that are currently being developed. These land-based sensors provide information of the location and the position of the ship. This data is fused over all sensors and merged into a customized visualization. The goal is to create a 2D picture of the overall situation of the surrounding of the relevant ship during the docking process. The ship captain can see his own ship's outlines, he can see the port structures, and he can see other ships in the area from a top view. And also additional information such as approach speeds, distance data, and environmental data will be made available and visualized via the system. In this slide you can see a harbor kai in Wilhelmshaven. The 3 red dots in the upper image indicate the sensor positions. Here on the right you can see a 2D view of the sensor data. The measuring points of the different sensors are shown here with the different colors. In comparison to the upper picture, there is now a ship at the kai. And as you can see, this ship is detected by 3 sensors at the same time. This allows an all-around view of the ship and its surroundings. And up to this point, the main responsibility in this project is with SICK, because high performance long range, and most importantly, reliable sensor technology is a must for such a system. The sensor has to deal with 3 main challenges in this application. The first challenge is the weather. On coasts, the weather is often unstable and rough. But it is exactly in these situations that we wanted to help the ship pilots with SmartKai. The second challenge is that we are dealing with large distances between the ship and the kai wall. And the earlier the ship is detected, the better the system can help prevent collisions. So we need measuring range. The third challenge is that there's sometimes a strong tidal range in the port. And in addition, storm surges can occur. So the sensor must reliably detect ships at all water levels and must not be destroyed by short-term flooding. The SmartKai sensor is a 3D sensor with 4 layers. With these 4 layers, it is possible to detect the position of the relevant objects at all water levels, and also different ship sizes. SICK is known for building robust sensors that perform for a long time in their applications. We also want to realize this in the SmartKai system, of course. For this, the housing is designed to be very robust and as waterproof as possible. So much for that. Now we move on to the overall system. In the next step, the data is merged so that an overall picture is created, from which information can then be generated. To continue to show it in color, this would now be the second image here, with the overall view with the white scan points. Let me show you a short video now. Here you can see how it all works up to here. The ship is approaching the Kai wall. It's a relatively small ship and quite fast, but just right for our testing purposes. In this case, testing was done with the LDLRS, but in the second step the whole thing happens with this new SmartKai sensor. In the lower half of the video you can see the fused sensor data of 3 LDLRS, and above the camera image of the same situation. Even at this stage, the captain could use this point cloud to dock the ship without looking out of the window. But we don't just want to provide customers with a cloud of points. We want to provide them with processed data and information. So we are now working on creating objects out of the points. You can see that here in the third picture. We can see 2 classified objects in the water and the port structure. After this object building, these objects can then be analyzed in their position and movement, and additional information can be included. This is the basis for the user interface and finally the maximum customer benefit. The visualization will then have the goal of displaying only the useful information and making it as quickly and intuitively understandable as possible. The whole thing is then variably adaptable depending on the user group. For the design of the user interface, we work closely together with the user groups, especially the port pilots and the port operators. These groups see particularly great added value in such a system. Our project partner office is also in close exchange with users and also active in other projects in the maritime sector. I interviewed Dr. Sebastian Feuerstack on this subject. He is principal scientist at Office, an associated institute of Karl von Ossietzky University in Oldenburg. He is leading the research group Application and Industrial Processes that focuses on the application of verification and validation methods to test automated maritime and automotive systems.
Mr. Feuerstack, where are we right now? Please tell us something about what we see here and what can be done in this room.
We are in one room of our research labs. I'm standing in front of one of our integrated ship bridge simulators, which is part of the eMaritime Integrated Reference Platform, EMIR. It has been specifically designed for performing validation and verification tests of future highly automated and autonomous maritime systems. Such simulators enable us to perform what we call scenario-based testing. Scenario-based testing will be relevant for system certification of future maritime systems, specifically if AI methods, such as machine learning, are used. The simulator is custom-built and can perform simulations much faster than real time. We also apply it to test the SmartKai system. There we focus on variations of critical berthing scenarios, those that are too dangerous to test in the field.
Mm-hmm. Are there other projects besides SmartKai in the area of autonomous shipping? And how do you see the technological trend?
We are currently seeing a lot of flagship projects in Germany and all over Europe that focus on autonomous shipping and demonstrate what might be possible in the future from a technological perspective. SmartKai is implementing a very different approach. It thinks the most critical situations, such as berthing and in-port navigation first, and then develops a solution that includes important stakeholders, such as the port operator and harbor pilots, from the very beginning on. We basically follow the perspective on preventing damage of port infrastructure and vessels at the same time. From this perspective, a shore-based assistance system is a logical consequence. It works for every ship, even those that are not equipped with the latest technology. SmartKai therefore supports the digitalization of the ports and the maritime infrastructure of, in our case, Lower Saxony.
Okay, very interesting. And how did the cooperation with DIC come about?
we got in touch at a conference in Hamburg. We demonstrated some research of a PhD student of our group that researched about generating maritime situational awareness pictures. There we used, besides other sensors, quite basic LiDAR sensors. SIG made us aware what is possible with the latest LiDAR technology. We also learned that they were working on long-range scanners, specifically designed even for rough port environments, full of mist and salty water.
What is your experience in the current project with the different SIG technologies?
Some months ago, we set up a first test campaign at the port of Wilhelmshaven, which is close by. As soon as we had seen the first LiDAR images, we got very impressed what is already possible with out-of-the-stock products, and are currently learning together what needs to be adapted to support berthing and log passaging of vessels. Now we are just preparing the next test, this time in Cuxhaven port, with the new long-range scanners, and also in addition to short-range radars that should support the very, very last meters. We are very much looking forward to seeing the first results.
The project completion of SmartKai is planned for 2022. What will happen with the project and the SmartKai system after that?
We already got so much amazing feedback from around the world. Most importantly, shipmasters and pilots are with us. Different to port radars and satellite-based positioning systems, we are now talking about centimeter-precise positioning that would massively improve the situation awareness of shipmasters and pilots, and will make berthing in tough situations, such as strong winds or at night, even more safe. And it's accessible. In the end, it just requires a tablet to support log and bridge passing, or the navigation in narrow port areas. Also, berthing will be even safer.
Mr. Feuerstack, thank you very much for your time and goodbye.
Yeah, thanks.
There are other approaches to avoid collisions with ships besides SmartKai. For example, sensors attached directly to the ship can help in certain cases. SIG is also involved in these other forward-looking projects. You remember the different sensors from the beginning in this presentation. The MRS 6000 is suitable for such a task thanks to its gapless 3D scanning. My colleague Sandra Wienbeck will tell you more about this sensor and a very special application in the next presentation. Thank you very much for taking a look and have fun with the further topics of the Sensor Ocean Conference.
So, thank you very much, Robert. That was really impressive what we can do with the LiDAR scanners, and I really like the last scene, this LiDAR scanner installed on a boat from the Fraunhofer Institute, and actually that was the port of my lovely hometown, Hamburg. The SmartKai project looks like a very innovative solution, and I think it's extremely helpful for pilots and operators to avoid damages on port and infrastructures. Right. Robert, we have two questions in the chat. First is, how does LiDAR perform in fog?
Oh, in fog. Yeah, we have, on the one hand, we have some technical measurement improvements, like big lens and a lot of laser power and such things. And we do also have some software features to improve the recorded data to use them for the SmartKai system, and makes that work also in bad weather conditions. But to get in detail on that would take too long for today, I think. But I'm looking forward to answer these questions afterwards.
Okay. And then we have a second question, and that is, how is your product different from the radar systems on board vessels that is used for collision avoidance?
The main difference is that if you use a LiDAR system, you know the exact position of the object which is detected. I think this is, to say it in short, the main difference. If you detect something with a radar sensor, you know there is something. But to know where the exact position is, you have to use a LiDAR sensor. Of course, there are a lot more differences, but this is the main, I think.
Okay. And then finally, the last question we have, that's quite interesting. Is this useful to identify underwater collision hazard like icebergs or similar?
This system is not useful for this, but there are other technologies, underwater radar and such things to do so. But the SmartCast system and our LiDAR sensors are above water level.